What's going on YouTube? So I got another one here. This one is the math behind font rasterization. Now I had started watching this one because I watch a lot of different videos on this kind of stuff. Again, just trying to really learn it. But I started watching it and there was a few things that I actually been using. I said, well, let me just record it and share this with everybody again in hopes that we all can learn something new. So the math behind rasterization, this is also done by Game with Gabe. I want to give credit to the original video. Here we go.
If you have ever written a document, read a book, made a PowerPoint presentation, built a website, or even worked with text in general, then you have used font rasterization. Font rasterization is the process of converting a vector description to a raster or bitmap description. In other words, font rasterization is converting mathematical formulas to pixels on the screen that you're using. We use this process every day when we use our phones, but have you ever wondered how it really works? Computers display graphics to us by using pixels on a screen. In the 80s and 90s, we had very limited resolutions because computing power was not sufficient enough to support a lot of pixels on the screen. Now, we have resolutions that can contain upwards of 33 million pixels on a screen. Compared to a Nintendo Game Boy, which only has around 23,000 pixels on the screen, this is insane. Now, why are we talking about pixels and screen resolutions? Because in order to understand the evolution of font rasterization, you must understand where we came from and where we are now. If I asked you how to represent text using a limited number of pixels, how would you do it? Well, the easiest way I can think of would be to simply plot the pixels in the shape of letters. This is simple and straightforward, and it's very easy to communicate to a computer that deals with pixels. So, plotting the letter A would look something like this. I could also plot the letter B, and so on and so forth. We can very easily calculate how much computer memory this would take up per character set. If we assume each pixel is represented by 8 bits, allowing a grayscale image to add some variety, and each letter is only 32 by 32 pixels, then storing the English alphabet would only take up around 425,000 bits. We know that 8 bits is 1 byte. So this would take up 53,000 bytes or around 53 kilobytes.
So in terms of game design, a lot of the old games, like it showed the Game Boy right there, which is funny, but I ran in bits like that. To really see that beyond the Game Boy, if you go back to the original Atari, it was running in bits. How many? I don't know. I gotta look that up and see what the power of the old Ataris was, but it definitely was not much. But it's interesting here how he's breaking down the alphabet in bits, because we type it and use that every day.
This is great. We can store an alphabet in a way that's easy to communicate to the computer, and it also takes up very little space on the computer. But there's one problem. What if we want a different font size? Unfortunately, our whole technique breaks down here. The process I just described is how the bitmap file format works, which was created around 1986. Around 1991, Apple decided to add support for a new font file format that would solve our problem, the true type file format. So, we must revisit our original question. If I asked you how to represent text using an unknown number of pixels, how would you do it? Before, we assumed you knew how many pixels you could use and it was limited. But now, let's assume that the user could use a 12 pixel font size or a 512 pixel font size. How do you represent the letter A for both of those? Well, you could create a bitmap file for both pixel sizes and switch the file for different sizes, but this is very inefficient and costly. A 512 pixel font size for the English alphabet would take around 109 million bits or 13.3 megabytes. We are now wasting a lot of memory for the different font sizes, and we are multiplying the amount of work for ourselves by having to recreate the font for every different font size. Instead, let's use math to solve this problem.
And so this is the interesting part right here. And this is actually the reason why, like, when you have a computer and it has a graphics card, why there's updates and tech that come out. And in some cases, or a lot of cases, your old graphics card can be reformatted in a way to where it unlocks better power, is more efficient, and the like, because it's doing stuff just like this but in code, which is crazy to think about. And just a simple, like it was just saying about how, like, lettering, the bigger the letters equal more bits equal excuse me, equal more bits equal more memory. And it's like, I think how crazy that is when you go to download a different font completely. So yeah, that's it's interesting stuff right here.
We know that you can represent curves in math using an equation. There are different kinds of curves that you can create. For example, a quadratic curve looks like this. A cubic curve looks like this. A logarithmic curve looks like this, and there are many more. We can also translate these curves by simply adding offsets to our equation. We can offset any curve vertically by adding a number outside the equation, and horizontally by adding a number inside the equation. We can do all sorts of transformations to our curve by modifying it slightly to get different results. Now,
Drawing with math. So this is very interesting too, because in Unreal Engine 4, the old way of doing effects, if you want to mess with some specific effects, you have to use those curves. So you have to actually change the math to get the curve, to get the effect to do what you want to do. So like, say you had fire coming, right? And you wanted the piece of the fire to be bigger, or you wanted to change color. Well, you would use a curve to actually change that. I never understood it until I saw this part of the video. I didn't finish this video. I watched like a little bit of it. I stopped right there, so I'm like, yo, it's interesting how, like, all these little bitty systems I've been using, I just didn't know what it was. Now it makes sense to me why those curves that you would move, you would bend them, twist them, not twist them, but you would like bend them and then move them up and down up a curve, and then what the whole graph itself means. Now I get it. Now I can go back, even though that effect system has been replaced with a new system called Niagara. You can still go back and tweak it, but now I understand what that whole graph is now. Oh, it's interesting. That's how you learn.
now we know two things. 1. We can represent any curve using an equation. 2. A letter is just a combination of several different types of curves. Now that we know this, we can set out to represent a font as a series of mathematical curves that describe each letter. But how do we do this? We could define a set of points that we want our curve to pass through. Then we could connect each of these points with a straight line. But for letters like C, this won't work very well because of the curvature. We could create a polynomial to pass through each of these points, and there are entire procedures to do this. One of these procedures is known as Lagrange interpolation, which will create a polynomial that will pass through all of your points. But this doesn't give sharp edges that are expected in a letter like capital A. So, we have two techniques that work for different types of letters. Why don't we combine them? That's exactly the process that the TrueType file format takes. It combines straight lines and simple second-order Bezier curves to describe a set of letters. A Bezier curve is special because it can represent a curve using a set of control points, P0 through Pn. Where P0 and Pn are the endpoints, and all the in-between points are control points. These control points describe how the curve should bend, and if we keep it simple with second-order Bezier curves, then we only ever have 3 points to describe a curve that only bends in one direction. Now, we have a solution. We can represent the outline of a letter using a series of points and a description that tells us whether the next 2 points are a line or the next 3 points are a Bezier curve. We have another problem though. Sure, we can draw the outline of the shape, but this does not help us draw solid letters. Remember, computers are made of discrete pixels, and all we have is a way to describe a series of curves that describes the outline of the letter. So how do we fill the letter in? Well, the simplest way we could do this is by drawing the outline first. This will give us a closed set of pixels which outline the letter. Once we have the outline drawn, we can simply pick a pixel inside the letter and fill the shape from there. This will work fairly well. However, when we get to a complex letter like capital B, we run into another problem. What is the inside of the letter? We intuitively know that it's these pixels, but how does the computer know it's these pixels and not the pixels inside the holes as well? Well, some clever mathematicians have already solved this for us. Let's look at this problem from another angle. Instead of drawing the outline, why don't we test each pixel to determine whether it is inside the outline or outside the outline? If we think about it this way, we can come up with a solution that should work. Notice that with the letter capital B, we can look at a pixel over here. And if we draw a line to the right, how many times do we hit a line? Well, we run into 4 lines. What about when we start inside here? We run into 3 lines. And what about in here? 2 lines.
Alright, so I'm going to stop the video here. This, as you can see, it's 16 minutes long. I'm going to do this in a 2-part. But, so in Blender, it's a 3D program that uses Python. It's crazy because everything you just showed as far as the Bezier curve, this right here, with determining the points, that's how you make 3D objects. So if like if you wanna make a shoelace, right, you'll make a Bezier curve to a point A to point B, and then you can extend it if you want. But just like you showed, you have a point here, you have a point there, and then you apply it. It'll turn that whole line into basically a solid tube or a piece of polygon. And then this right here, how you show, like with the A, like those points in Blender represent a vertice. So you put a vertice there, then you can draw a line and draw another line, and if you fill it, like 3 lines, right? Like if you had a vertex here, and a vertex here, and then you go to fill that, it'll make a triangle. And in this case right here, if you have like the E shape, like in Blender, you can literally take a point and make that E and then fill it and it'll turn into an E. And then when the points aren't aligned, you fill it, it gets all the polygon that it makes from the vertice is off balance because it doesn't know where to fill it in at. And then this line cut that he's doing right here, that's literally called a line cut in Blender. So you can take a piece of polygon, put a line through it, and then apply it, and it'll put a cut through it, and also it'll put 2 new vertices in each part and make a line. What did you call that line here? But yeah, this is super, super interesting because it's like I've been doing this for the past 5 years and didn't know that this is like, this is what is computing as I'm doing that. Video 2 on the way.